All right, so this is section 11.4. We're continuing on with our tests for convergence and divergence, and this specific section is called the comparison tests, and it's plural because there's two different kinds of comparison tests that we're going to talk about. In the first video here, we'll talk about the direct comparison test and how to apply that one, and then the second video, we're going to talk about the limit comparison test and how to apply that one. I think that the direct comparison test is probably the most intuitive as to how and why it works. The limit comparison test maybe not quite as intuitive, although it does mathematically make sense, but it's probably easier to perform. So let's get to it. The idea is, as the title says, we are going to compare things. What we're going to do, um, I'm going to go ahead and sketch a graph here. The idea is we've got some kind of a series that we're going to basically change into a continuous function. And it's going to look something like this. It's got to be approaching 0 as the n values or the x values get really, really large. And we're going to call this our given series, a sub n. Okay, so that's the given series. That's the one we're trying to figure out, does this converge or diverge? The idea is, remember that for something to be convergent, it has to approach 0 at a fast enough rate so that we can basically find a sum. If we know another series which is similar to the one that we are looking for, and we can somehow bound it one way or the other depending on which way we're trying to do this, then we can tell something about the series. So what I mean by that is, let's say I think that a sub n is convergent. If I can find a greater series than a sub n, for example, maybe this one right here, we'll call this a b sub n. If I can find a b sub n that I actually already know is convergent, because if we're saying that the red one, b sub n, goes to 0 fast enough that it can find a sum, well, anything else that is already approaching 0 at a faster rate, or by looking at it graphically, is less than the b sub n, it has to approach 0 fast enough, because if b sub n already approaches it fast enough, then anything that's less than that's going to approach it even faster. So we're basically saying, if I can find a b sub n, which is going to be convergent, then any other series which is less than or equal to b sub n is also going to be convergent. So we're going to compare our a sub n to a known convergent series that is greater than a sub n. The question becomes, what if I think that a sub n is convergent, and then I say, okay, well, I'm going to pick a b sub n or some other kind of thing, but it's less than instead? Well, in that case, we actually don't know anything. Maybe the orange one is convergent, but because a sub n is greater than that, we don't know if a sub n is convergent or not. You would have to basically bound it from above in order to stay convergent. Now, conversely, if we think that a sub n is divergent, so it's not going to approach 0 fast enough for us to find a sum, then if I find an orange one, and I'll call this also a b sub n of some kind, if I find the orange one which is divergent, but it's less than a sub n, well, by virtue of the fact that b sub n is already divergent, anything that's above b sub n also has to be divergent. Now, if I think that a sub n is divergent, but I find a b sub n, which is in the red, which is divergent, again, because it's above, that doesn't do anything. So it really just depends on which way you're trying to push the series that you're trying to find. Okay, so I hope intuitively that makes sense. So if we are thinking, and this is where you're going to have to draw a hypothesis, actually. You're going to have to hypothesize, what do I think is going to happen? And I'm going to give you ways to look at it, which hopefully should make some logical sense. But that's the general idea. So it says in our criteria right here that if B sub n, number one, if B sub n converges, then the sum of A sub n is also going to converge. And that's if B sub n here was greater than A sub n. And then it says that if A sub n diverges, which is the one that we're looking for, then B sub n will diverge because it's bigger than that. So again, hopefully intuitively that makes sense. I think it's the easier one to figure out. And you can read these paragraphs down here, and I think that kind of explains what we're looking for. Let's go through a few examples, and we'll see how this works. So the procedures, you're going to find the simpler series and evaluate for convergence or divergence. And what you need to do, and this is the hardest part, is you need to pick a series which is very simple. Like nothing you would have to use another test to do other than a basic, oh, I can look at that one. That's a P series. Oh, I can look at that. That's geometric. Piece of cake. Then you're going to compare it with the function according to the rules that we talked about. All right, so this is what we're going to do. Number one, we're given the series 1 over 2 plus 3 to the n power. We want to know whether that's convergent or divergent. The first thing you should do is you should hypothesize in your mind. Do you think this is going to be a convergent or divergent series? Well, my hypothesis, and this is the way I would look at this, is I've got a constant on top, and my denominator is growing at an exponential rate. 3 to the n is going to be an exponential growth. So the denominator is going to grow very, very fast. Remember that our cutoff was 1 over x to the first power, or 1 over n to the first power, or 1 over n squared, or anything, 1 over n raised to anything greater than 1 would be a convergent series. Anything 1 over n raised to the power of less than or equal to 1 would be a divergent series by a p-series test. So again, 1 over 3 to the n, that grows much faster than a 1 over n to the power, or some kind of polynomial or power function. So my hypothesis is this is going to be convergent. So we think it's going to be convergent. What we need to do is we need to find a greater series that we know is convergent and then compare the two. So I've given us this one in this case. So this one here, we can say, okay, this resembles a geometric. It resembles a geometric if you remove the 2. So that's what I'm looking at, is saying, okay, well, if we just get rid of that 2 in the denominator, then it looks like a geometric series. So we're going to use the series 1 over 3 to the n, which then can also be written this way. Which is definitely a geometric, where r is 1/3, and we would know that that's convergent. So we're calling this 1 over 3 to the n. This is the one that we're coming up with, because the given one is the one on top. We're calling this one our b sub n. So I'm going to say that b sub n is the series of 1/3, that's a 1/3 to the n, and goes from 1 to infinity. That's our comparison series. Well, from this, and we do have to state the criteria, this one is geometric, where r is 1/3, which is less than 1, and therefore convergent. So the one I picked, I know is convergent. Now, why did I pick that one specifically? Because I know that 1/3 to the n is greater at all times than 1 over 2 plus 3 to the n, because the extra 2 in the denominator of the one that's given to us is going to make our denominator bigger, which makes the whole fraction smaller. And you have to state that. So we'll call this one up here our a sub n, the given one. And then what we have to state then is, since a sub n is less than or equal to b sub n, and b sub n is convergent, then a sub n is also convergent. Again, I hope that that makes sense. Now, in this case, I gave us the b sub n. You're ultimately going to have to try and figure those out. And it's not always easy. What you can see is the only thing that I changed from a sub n to b sub n was this piece. I just removed that piece right there. Okay, you don't want to try and do something where you have to remove 2 or 3 different things because that's really difficult to prove. Try and find one alteration that makes it the way you need to make it. Okay, so we're going to determine the convergence or divergence of the sum of n over n plus 1, n going from 1 to infinity. Could I use comparisons? Yes, I could use certain comparisons maybe. It's probably a little bit harder, but you always have to think back to, okay, is there something easier to do? Is there an easier way? Well, remember, the first thing you should probably try on these things is taking a limit as n goes to infinity of n over n plus 1. Well, that limit is 1 by the nth term test for divergence. Since that does not equal 0, a sub n is divergent. Okay, not a lot of work to do there. We'll call that our a sub n again. We'll label that way. So remember, try some of the easier tests first if possible. Okay, in number 3. Okay, there's no easier test. Your limit here as n goes to infinity is going to be 0, which is inconclusive. This doesn't fit the criteria for any of the other things that we've done so far. Certainly don't want to try an integral on this one, that's for sure. But what it does resemble, again, we'll call this a sub n, what it does resemble is it resembles a p-series. If I just get rid of that plus 7 part under the square root, it's going to look just like a p-series. So let's write that out so we can see it. So we're going to call b sub n the sum as n goes from 0 to infinity. Actually, that can't be 0 because if I'm removing the 7, it won't work anymore. Of 1 over, it'll be the square root of n to the 5th, which you can rewrite as n to the 5/2 power. Now, looking at the original one, if I'm thinking about this as being a 1 over n to the 5/2 power type of thing, I'm thinking, okay, that kind of resembles a p-series. P would be bigger than 1. I think this is going to be convergent. Now we need to come up with a greater known series that is also convergent. Well, this 1 over n to the 5/2 is greater than our a sub n because of the plus 7 in the denominator of the a sub n, making it a smaller overall fraction. So we now have a b sub n, which is a p-series, where p is 5/2, which is greater than 1, and therefore convergent. And since we know that b sub n is going to be bigger than a sub n will also be convergent. So since b sub n is greater than or equal to a sub n, oh, skipped a step, and b sub n is convergent, then a sub n is also convergent. Okay, and that's kind of the steps you want to go through there. All right, let's look at example 4. Determine the convergence or divergence of the sum as n goes from 2 to infinity of the natural log of n divided by the square root of n. Again, this one's not as easy to determine. If you were to first start off by taking the limit, I'm not going to write out the process here, but you eventually get 0 using a couple of L'Hopital's rules. So that's inconclusive. That doesn't tell us anything. This does not fit the criteria for any of the other things, geometric, p-series, all that kind of stuff, but we can remove just one piece of this and have it resemble a p-series. So if we just take out the natural log of n part, so again, we're going to call this part a sub n, we're going to define our b sub n, n equals 2 to infinity for our sum. as 1 over the square root of n. The square root of n is the same thing as n to the 1/2 power. So now it looks like a p-series. Okay, because of the way the natural log of n and the square root of n grow, I would personally think that because they grow very, very slowly, and they're very similar, I would think that this would probably be divergent, but we're going to find out pretty quick. We are now, because I think it's going to be divergent, we're now looking for something which is less than a sub n, but is also divergent. And if that's the case, then a sub n would have to be divergent, because if it's bigger than b sub n, which is divergent, a sub n has to be divergent as well. So 1 over n to the 1/2 power is a p-series, where p is 1/2, which is a number less than 1. Therefore, it would be divergent. So we're now defining that b sub n is divergent, and b sub n is going to be a series which is less than a sub n, because in this case, b sub n and a sub n's denominators are identical, but a sub n has natural log of n on top, which is going to grow. It's not going to grow fast, but it's going to grow faster than 1, which doesn't grow at all. So a sub n is going to be a greater series. So we would say since b sub n is less than or equal to a sub n, and b sub n is divergent, then a sub n is also divergent. Now, some of you may have looked at this problem and said, that's not going to be true for every possible value, and you would be correct. As a matter of fact, this doesn't actually happen unless n is bigger than or is bigger than e, which means basically n would have to start at 3. At 2, it's not actually going to be a true statement, but from 3 on, it will be. So the idea behind that one is, as long as there is some kind of a finite value for which this circumstance happens for the rest of the values on, and it doesn't fluctuate back and forth in any fashion, it's okay not to necessarily start at 0 or 1. The first couple of terms could be off, but you will see that after a certain term, it will be that way forever. All right. Number 5. Here we've got 1 over n raised to the square root of n. If you remember something where you've got a variable raised to another variable, this is what is called an iterated function. And iterated functions tend to grow very fast. So that means if your denominator is growing very fast, it should approach 0 much, much faster than most of the other ones. And this should be a convergent function. So we want to find something else which is convergent, that is also going to be a greater function than this one, for all n values past some certain point. This one's not as easy to figure out. In this case, your b sub n should resemble some kind of a 1 over n to some power. So it's going to look like a p-series. You would just have to figure out what power it is. Well, we think it's going to be convergent, so picking 1 over n makes no sense, because 1 over n is divergent. 1 over n squared might work. Let's try it. If it doesn't, we'll try something else. So we know that 1 over n squared is a p-series, where p is 2, and since that is greater than 1, b sub n is convergent. So now we have to show is that b sub n is greater than a sub n for all n values past a certain point. So we're going to say b sub n is greater than or equal to a sub n, but is that really the case? So let's pick 1, because that's where these series start. If I pick 1 and I put 1 into n's for both of these series, I get 1. Okay, well, that means they're the same there. What if I pick 2? If I let n equal 2, in my b sub n series, here, plug 2 in for n, you get 1/4. Plug 2 in here, this is not easy to tell. I'd have 1 over 2 raised to the square root of 2. 2 raised to the square root of 2 is not going to be quite 4. So in this case, it's not actually working yet. This won't actually work until you get to 4. After n equals 4, everything will work. Because if you plug in 4, you're going to get 1/16 for b sub n. If you plug in 4 for a sub n, you also get 1/16. After that, all the numbers that you're going to plug in for n are going to work. So from here, we would just say that that is the case for n is bigger than or equal to 4. And then you would continue, and we already determined that b sub n is convergent. That is horrible. Okay, not much better, but a little bit. Therefore, a sub n is also convergent. All right, I think we got one more example, and then we'll come back with the limit comparison test. So determine the convergence or divergence of the sum of 7 to the n plus 2 over 6 to the n power. Again, your hypothesis should be, well, it looks like my numerator is going to be growing faster than my denominator because the dominant terms are 7 to the n and 6 to the n on the numerator and denominator, and 7 to the n, of course, is going to grow faster than 6 to the n. So really, this should be approaching infinity, which means that it's going to be divergent. And you can actually do it this way, because you can just simply take the limit as n goes to infinity, as n goes to infinity, of 7 to the n plus 2 over 6 to the n, which is approaching infinity, which is definitely not 0, and therefore this would be divergent. The other way you could do this one, if you wanted to actually use a comparison test, I'm not going to go through the full thing here, but you could split that sum. You could make this the sum of 7 to the n over 6 to the n goes from 0 to infinity, plus the sum as n equals 0 to infinity of 2 over 6 to the n. And what you would do here is you would basically say, oh, let's look at this first one and say the first one is the sum as n equals 0 of 7 over 6 to the n power. That's geometric. By using some of our properties, we can pull that 2 out of the second one out to the front, and what we would have left is the sum of 1 over 6 to the n, which can be written as 1 over 6, the whole thing to the n, which is also geometric. What you end up getting here is a divergent geometric series plus a convergent geometric series. Anytime you have a divergent plus a convergent, the whole thing is divergent. Okay, you cannot have a divergent plus a convergent and have it somehow converge. That doesn't work. So that's a second way to do it. All right, that is plenty enough for this video. We're going to come back with a second video and talk about the limit comparison test.